Glucagon binds to its receptor. The glucagon receptor is coupled to a G-alpha stimulatory protein. You learned all about that. That G-alpha stimulatory protein you know all the way to there. Stimulates cyclase. Stimulates cyclase converts ATP into cyclic AMP. The cyclic AMP activates pKa. The pKa then phosphorylase an enzyme called phosphorylase kinase. So it's a kinase, it's a kinase that phosphorylates a phosphorylase. I don't like this stuff, I just teach it to you. So this phosphorylase kinase sorry, it's getting crowded. This phosphorylase kinase, phosphorylase glycogen, phosphorylase, which in its active form is called phosphorylase. And that ultimately leads to the production of glucose 1-phosphate from the glycogen. So it starts liberating glucose from the glycogen. It effectively starts increasing glucose in the cell so that ultimately the glucose, should I draw this all over for you again? Yeah. What time is it? Do we have time to do that? Oh, yeah, we're good. All right, let's do the whole thing. So in the liver, let's see if I can explain this better. So in the liver, here's what insulin's done. The glucose is coming in through the glucose transporter, through the GLUT7 in the liver. The insulin binds, the first thing phosphorylated is IRS1. IRS1 ultimately phosphorylates hexokinase. The glucose is converted into glucose 6-phosphate. The dismutase turns it into glucose 1-phosphate, and then it's packaged into glycogen by glycogen synthase. And the two regulating ones are primary hexokinase and dismutase. The glucagon, let's put the glucagon way over here so we have room. also used to be called phosphorylase B. That's the other name for it, you might know. And this active form of phosphorylase phosphorylates the enzyme that goes from glycogen to glucose 1-phosphate. So you start pulling the glucoses off, and then basically you reverse this process, so now the glucose starts flowing back out. Does that all make sense?
Does it cause the glucose to leave, or does it just change the gradient so it doesn't come in?
Well, it doesn't, so remember, here's what's happened. Glucose has gone up, it's caused insulin to go up. If insulin's going up, it's inhibiting the glucagon, right? And the glucose is going into the liver cell at that point because glucose was high to begin with. Otherwise, the insulin wouldn't have gone up. Does that make sense? If the glucose goes down, insulin goes down, so now you get the glucagon, but now the insulin concentration in the blood has gone down. So by glucagon liberating glucose from glycogen, you're generating a higher glucose concentration inside the cell. And I believe it goes straight out through the same glucose transporter. It just goes back down its gradient. So you've changed the gradient because insulin changed the gradient. And now glucagon is reversing that by liberating glucose back in the cell, by breaking it away from the glycogen. Questions or comments? Because it's going to get a little bit more complicated. Yeah?
So sorry, is the phosphorylase A actually phosphorylating like the enzyme? So GS or no?
Which? No, not glycogen synthetase.
Okay.
It's a separate enzyme that takes it backwards.
Oh, okay.
Pretty sure.
So it's activating the enzyme that does it.
I'm pretty sure phosphorylase A does it directly.
Okay.
But it's not, the glycogen synthesis, I think, only goes this way. So you're reversing the process, but it's a different enzyme for the liberation. We're good? Okay, so somebody already asked what you do with that glucose. You have time to do that? Huh? Oh. So what we'll talk about in more detail tomorrow, or Thursday, is what you actually do with the glucose. In some cases, you store it. If you're taking in too much glucose, of course, you ultimately store it as fat. It's going to be moved around. We already talked about this. It's going to be moved around to different places if you're pregnant. Do the interactions with other hormones. If you're growing, it's going to be moved around and used differently as well. So digestion involves breaking down complex molecules, proteins, carbohydrates, and fat. And bring them into your body as free fatty acids, simple sugars, and amino acids. Intermediary metabolism is how you convert these small molecules back and forth into larger and smaller molecules. A lot of people in common language use metabolism often when they really mean digestion. Metabolism consists of let me erase this. Metabolism is kind of breaking down and anabolism, which means building up. Like when people talk about anabolic steroids. So anabolism would be the conversion of amino acids to proteins. The conversion of simple sugars to complex carbohydrates, like glycogen. And the synthesis of fat for storage. You can convert sugars into amino acids, and you have to burn sugar or fat for any anabolism. Anytime you build something, whether it's protein or complex carbohydrates or fat, it takes energy to build those larger molecules. You can convert simple sugars into fat, but not the other way around. If you're in a high-fat diet, once you take it in as fat, you can do nothing but store it as fat. You also can't burn it. So whereas you can eat pasta, carbohydrates, and run around and burn it right away, fat has to be stored before you can utilize it. This is all anabolism. This is all catabolism. If, for example, you were on an extreme diet, you would first catabolize complex carbohydrates. So when you run, you have to, for example, if you're on an exercise regime where you're starting to lose weight, you don't start burning fat until at least 20-30 minutes of sustained aerobic exercise. You first burn carbohydrates, then you switch to burning fat. And if you're not eating well when you're exercising, or if you're in some starvation diet, ultimately you'll start catabolizing protein to generate energy stores to keep your body alive. So we talked about a few hormones already that are involved. You know that insulin promotes anabolism of simple sugars. You know that glucagon kind of does the opposite. Insulin also promotes the storage of fat. And insulin supports anabolism of amino acids, the building of protein. So for example, I told you that insulin was kind of like the growth hormone for the baby. So it's promoting glucose uptake, amino acid uptake, and protein anabolism. You can also put some more hormones up on the board. All right. If you go to prolactin, wants to maintain high blood sugar. It promotes glycogen breakdown Prolactin also promotes fat breakdown. And it's doing that under these special circumstances where those energy stores, rather than store the energy, it wants it to go either to the baby or it wants to go to the mammary gland. You know, the growth hormone promotes the same catabolism. But growth hormone does that in conjunction with IGF-1. So while growth hormone is promoting catabolism of carbohydrates and fat, the IGF-1 is promoting the conversion of those energy stores for protein anabolism. Thyroid hormone, very important. Thyroid hormone promotes the burning of fat. People who are hypothyroid, we'll talk about on Thursday, tend to be overweight and store fat, have a very low basal metabolic rate. You have a question? At the same time, thyroid hormone also promotes carbohydrate catabolism, but it promotes protein anabolism. So again, it's moving your intermediate metabolism to burn fat and to burn carbohydrates so that those energy, or not burned, catabolized, so that those energy stores can be used for building protein. Good? Also important in catabolism is cortisol. But cortisol promotes the catabolism of everything. So under long-term stress, cortisol will promote the burning of first carbohydrates, then fat, and ultimately muscle wasting due to cortisol's catabolic effect on protein in the muscle and bone. Long-term stress can actually cause you to lose protein, well, you lose calcium from the bone, but primarily because you're losing bone matrix. We're good? And finally, or at least all the ones that I can think of right now, androgens tend to be protective of bone and promote I'm just going to call it testosterone, and promote protein anabolism. But there's a great deal of evidence now that the anabolic effects of androgen, of testosterone, on muscle is because it blocks cortisol from causing the catabolic effect. That's why people with AIS still have lean, you saw the picture of Samir. That's why they still have lean muscle, because it doesn't require the androgen receptor. It's androgens being anabolic because it's blocking the catabolic effect of cortisol. We'll put those all back into context on Thursday. Questions or comments? So I'll have like regular office hours tomorrow, 8:30 to 9:30. If you need a different time, if you need earlier, if you need earlier, or if you need later, email me. We're good? See you Thursday. You get a few extra free minutes this evening.